Thank you for coming. um, what I want to do is to tie up several mathematical strands. The way here on the plane, I planned this talk. I wrote down talk about, and I wrote, next to each thing, how much time do I think each will take, and I added them up. It's 275 minutes. To ask questions. I'm not going to talk. So what I want to start with is a silly question. Okay? I'll just denote gamma in this lecture. Okay, so in general, I'll give you an example. I don't want to talk in general. SLDZ. Okay, this group, for the experts, you can take high rank lattice. But that's a great example. And the question is, how many representations does this group? It's a discrete group. It has representations. How many representations does it have? Let me ask a correct question. So let's denote by Rn gamma number irreducible representations of dimension or degree less than or equal to n. Okay, so I'm going to take d greater than 2. Okay, d equals 2 is SL2Z is almost a free group, and nothing that I talk about will work here. But if you take d greater than 2, then this number is finite. Not clear? Okay, it was proved, I think, first time by Brenner, and in general, the generality of lattices by Weil. This is less than infinity. And the question is, how does this sequence grow? Okay, first of all, it's monotone sequence. That's that. And the question is, how fast does it grow? Okay. Now, this is a silly question, right? What am I asking here? I'm asking here, if I have a group gamma, I'm asking how linear is gamma? How many? So a linear group is a group of matrices, right? And I'm asking how linear is this group? Right? But this is SLDZ, right? It's group of matrices. It's as linear as it can get. Right? But see, it turns out that this question leads to lots of interesting mathematics. Most of which I'm not going to tell you. Okay, so several people worked on this. For example, Uri worked on this quite a lot. These questions, so if you have questions about other results, you can ask Uri next talk. But let me give you just a small sample of results. Alex Lubotsky and Ben Martin proved that the sequence grows polynomially. Some constant depending on gamma. Okay? And then a few years later, Michael Larsen and Alex Lubotsky he proved a lower bound. So they proved two things that are relevant. One of them is a lower bound proved. So this means that SLDZ is not too linear. Okay, doesn't have that many representations. And they proved that is at least somewhat linear. This is greater than some constant, of course, n to the 1/15. Were I too small? But another thing that they proved, which is more relevant to talk now, is the following. They proved something quite amazing. They proved that if you look at the number of irreducible representations of degree less than or equal to n that have finite image, okay, so the standard representation of SLD does not have is injective. It has infinite image. But there are, you can take this group, factor it through a finite quotient, then take a representation. Okay, that would be an example of a representation with finite image. Okay, so if you look at irreducible representations with finite image, divide by the number of all irreducible representations up to dimension, up to degree n, and they prove that this converges the constant, which is strictly bigger than 0 and strictly less than 1. Okay, so if you take one of those groups and you look at all representations of dimension at most 1,000, well, 1 million, generous, and you ask how many of them are, have finite image, answer is, 70%. Raise this. So if I'm looking at irreducible representations of degree n with finite image, it means that these are the representations that factor through the poor finite completion, gamma. So this, let me write it more succinctly. This. So I'll give you an example, just sort of numbers you get. If your gamma, so I know to compute this thing, in the case of group, it's not exactly SLDZ, but SL2 of Z, square root of 2. It can be other quadratic fields here. Or, you know what? I will know the answer in the case of SL2 of no, I will know for other numberings. No, but for this case, get that Rn of SL2 D square root of 2 or finite completion divided by Rn of SL2 square root of 2. Another one. This converges to 36 over pi to the fourth. Pi to the fourth is about 100, right? So this is 36%. This means that if you want to count all representations of gamma, basically now, if you want to show how fast does this sequence grow, it's enough to count only representations with finite image. Again, or representation that factor through the poor finite completion. But the poor finite completion Z of SLDZ is just a product SLDZP. So you're basically, I'm simplifying the question, it doesn't look like it, but I'm simplifying the question. I'm asking, instead of counting representations of SLDZ, which is a discrete group, I'm led to asking how many representations does SLDZP have? This is a compact group. This is an almost 4P group. Much better, much easier question. So let me shift gears. So remember, I'm interested in representations of this group. So let me shift gears and go to Frobenius. In 1806, Frobenius invented representation theory, and he knew the first thing we tell students about representations, namely that if you look at the sum, look at all irreducible characters. So G start with a finite group G. You look at all characters look at their degree squared, sum of these numbers is the size of G. Okay, the second thing we tell our students is that the number of characters is the number of conjugacy classes of G, right? Let me write it in a funny way. Okay. This is the number of conjugacy classes of G. But now when you look at it, right, this is the second moment of some vector, the vector of dimensions. This is the 0th moment of some vector. What about the rest of the moments? So Frobenius knew this. So this is theorem of Frobenius from 02, it's 1902, that prove that if G is finite and there's some integer by G, then you look at this sum. Okay, so you can get the second moment, the 0th moment, the minus second moment, and so on. Okay? If you look at this sum, then the answer is, let's see. Easiest way, the more concrete way to write it is a number of solutions to some equation. So I'm looking at all x1 up to xg, y1 up to yg in g to the g, such that some equation holds x1, y1. This is the group theoretic commutator times xg, yg. The product of all of these commutators is 1. Okay? So think about what we have. We have 2 g variables in one equation. Okay? We expect that the number of solution would be the size of g to the 2g minus 1. Okay? So let's take a size here. Divide it by g to the 2 minus 1. And that's the answer. The answer is this number. I can be more fancy or short and note that this number is the number of homomorphisms from a surface group. This is a surface of genus G. Right, so the fundamental group of surface of genus G has 2 G generators and one relation. But specifying a homomorphism is just specifying where do each one of the generators go, subject to this relation. And again, divided by G to the 2 minus 1. Let me rephrase it again. Probabilistically, I really like the as a question in probability, as a probabilistic expression. Okay, so I saw one of the posters in the session that about random walks in groups. Is the person? Okay, anyway. So maybe none of you are interested in this, but I'll say it anyway. So that's the probability that if you randomize 2 G elements and then look at their commutators, okay? So what is a random commutator? I randomize X uniformly, randomize Y uniformly, and take the commutator, okay? So this is what I call a random commutator. That's the probability that the product G random commutators And this I should compare to the probability that the random element is 1. So that's the same answer. And if you haven't seen the proof, if you don't know this, then it's much more important than anything else that I tell you. So I'll go ahead and prove it for those of you who haven't seen it. Okay, so in order to prove it, I'm going to define something. I'm going to define a function. So fg, I define it to be just the number of pairs that commute to G. And this function is invariant to conjugation. So I can make sense to look at its Fourier transform. I can look at Fourier transform of f at the character chi. What do I get? So definitionally, I should take the sum over all elements G, f of G times chi of G. So I'll be off by normalizations of powers of G. A good exercise to correct me. Okay, but I can also write it as going over all pairs x and y. For each one of them, computing the character of the commutator of x and y. So each pair gives me, raises the corresponding f by 1. But chi is afforded by some representation, right? I'm going to write it. So instead of writing this, I'm going to write trace of rho of the commutator. Write it. This is trace rho of x, rho of y, rho of x inverse, rho of y inverse, which I can write first sum over all x, and look at the trace rho x times a sum now of matrices. All y, rho of y, rho of x inverse, rho of y. Now look at this matrix. Call it A. It's invariant to conjugation by all elements of rho G, for all G. This is an irreducible representation, right? So this is the scalar multiple of the identity. What is this constant? Let's take trace to both sides. If I take trace, on the right-hand side, I get alpha times trace of identity, right? Trace of identity is chi of 1. Left-hand side, so not left, the upper-hand side, this is a sum of G matrices. Each one of them is conjugate to this one. We get G times the trace of each one of those matrices, but this is just chi of x inverse. Okay? So I just have all this expression, alpha just is taken out. Right? This is sum over all x of trace rho of x, let's write it, chi of x, times alpha, right? Times G times chi of x inverse divided by chi of 1. Okay, now orthogonality of characters tells you this number is G divided by chi of 1. Probably G squared. So what does it mean? Let's go back. I know what the Fourier transform of f. I can write f. F of G is sum over all characters of this number, g divided by chi of 1 times chi of g. In particular, I can plug in g equals 1. Sorry, so this is incorrect, so this should be chi. So this should be g. In particular, I can write down f of 1. Remember, f of 1 is one of the things we want to prove. It's the number of pairs that commute g is equal to sum over all chi of the size of g, right? This is the number of irreducible characters times g. Sorry? So if you look at this inner product, okay, sorry. Maybe if you look at this, you're right. If you look at this inner product, then the inverse Fourier transform I should divide by g. Okay? Okay, but now I can look at, I can convolve f with itself. Okay? When I do this, I get a big expression, and I should compute the convolution of chi and tau for different characters. But there are different characters. When they are not equal, the convolution is 0. These are idempotents. They are 0, the answer is 1 over is chi divided by chi of 1. Okay, so what you get, you get, this gets multiplied by itself. This is g squared. Chi of 1, 3, chi of g. And again, I can plug in 1 and get on one hand, this expression. This is, so I should, again, convolution, it's not, the convolution of two things is g divided by the character. This is 3 times the sum g. Now, on the other hand, what is the convolution of this function with itself? It's a number of pairs of pairs, right? Quadruples, that at x, y, the x commutator y times z commutator w is equal to g. This function really is the number of x, y, z, w, that x commutator y, z commutator w, and so on. Okay, so if you take 3 times convolution, you get next moment. So okay, so there are a few points that maybe I'll say not right. First of all, this is really awesome, right? You haven't seen this. Second, even if you have, this is a very weird formula, okay? Once, okay, let's look at this. What's this? This left-hand side tells you something about homomorphisms from G to something. The representations of G. You're counting funny weights, representations into linear group, homomorphisms to linear groups. This is a count of homomorphisms to G. Okay? A totally different group, right? Surface. Another thing that's cool about this, maybe even more philosophically, it's, again, this counts representations. Okay? Now, this, think about this as some measure of how non-abelian your group is. If your group was abelian, then every commutator would be 1. Product of G random commutators would be 1. And this measure would be very singular. The random variable that is the product of 7 commutators will be very singular. So what this, and the more regular this measure is, the farther your group is from being commutative. So what this tells you that a group with few representations, a group which is very nonlinear, is also very far from being abelian. Okay, so so how is it connected to counting representations? So it gives you the following idea, okay? Here with 2 parts, if you want to bound the number of representations of, say, SLD ZP, first you want to find a geometric meaning the following sum. You look at the sum of all representations, now not of the finite group, but of the profinite group. Minus 2k, okay? Then, let me write it differently, okay? Instead of summing over all characters, I'll sum over all possible degrees of characters, okay? This is the number of E-reps of dimension 3. Exactly n times n to the minus 2k. And then you want to prove that this sum converges. You want to show that the geometric meaning, show that this sum, using the geometric meaning, of course, prove that this converges. Now this is an infinite sum, okay? For a finite group, it has infinitely many representations. If an infinite sum converges, each of the terms 0. So you get that the number of irreducible representations of degree exactly n is little o of n to the 2k. To find the k such that this converges, found the representation growth. Okay, so it turns out that one is easy, okay? I forgot to say this is based on joint work with Ami Eisenbad. To prove the following theorem, okay. For that, let me just give a few notations. So I have a map, call it IG, from SLD to G to SLD. So these are the algebraic groups, okay? Algebraic groups SLD, which, you're not going to be surprised. Take x1 up to yg, x1, y1 up to xg, yg, sends it to x1, y1, g, yg. And one important fiber of this map is one important fiber of this map, the fiber of 1, okay? These are all the 2G tuples of matrices whose product of commutator is 1. The variety of homomorphisms from a fundamental group of genus G to SLD. Okay, and it's usually, and people in geometric group theory call this the deformation variety of surface of genus G inside SLDZ, inside SLD. So if I write here, can people see in the back? No? You can please say something. So the theorem, what? You cannot, oh, thank you. Okay. You see if I write here? Was I? So this infinite version of Frobenius, the following. Look at the sum of, this is not a hard theorem, okay? This is just a restatement. If you look at the sum over all irreducible representations of SLD ZP, we actually have two expressions for it. First of all, you can look at the formation variety, all homomorphisms, and take Z mod P to the n points. You can ask how many elements does it have? Okay? This is a variety of a certain dimension, and you expect to have this many stations. Am I writing too small? Yes, okay. Am I writing too small now? Okay. Expect it to have this many points. Okay? If you take the limit as n goes to infinity, you get this number. This is really a restatement of Frobenius. Something slightly more complicated, but more useful, is the following. You have a map, okay? So it gives you a map between SLD ZP to the 2G to SLD ZP. These are actual groups, not algebraic groups. They are compact groups. Each one of them has a Haar measure. You can look at the Haar measure of SLD ZP to the G, the 2G. So you have a measure on one group. You have a map from one group to another. You can push forward this measure. Get a measure on SLD ZP. Okay? You have another measure on SLD ZP. That's the Haar measure. And ask whether they are related somehow. Okay? And it turns out that this measure is always, in this case, is absolutely continuous with respect to the Haar measure. Look at a Radon-Nikodym derivative. It's been a long time, right? Since you have it. If the Radon-Nikodym derivative of this measure with respect to this one. Okay? And this is a function. It's an L1 function in general, but value at 1 is exactly the sum. This is what happens when you take this this expression, this equality, and push it to the limit. Limit as the depth go to infinity. So what does it help you? Okay. So one thing I want to say about our measure on these groups are given by integration of differential forms, absolute values of differential form. This is a slightly delicate issue even for R. So you know that if you have, if you have a manifold, real manifold, with a differential form on it, you can integrate it. This is not quite a measure because it depends on the orientation that you choose, right? With a different orientation, you get the minus answer. Nevertheless, you can get a measure out of a differential form. You take the absolute value. You want to know what you have your manifold, you have your differential form, you take this here. You don't know what is the measure of this piece. Then you can just integrate omega on this piece, get, either if you get a positive number, you say, okay, that's the number. If you get a negative number, you take the inverse, the minus. Okay? And a similar thing you can pull, and a similar trick you can pull off in p-adic. Trust me. And the Haar measure is one of those examples. Haar measure, if you take a top form invariant to, which is invariant to the action of the group, then what you get is a Haar measure. Okay, the measure you get from an invariant top form is an invariant measure. So you can ask more generally. Okay? There's a more general question. Okay, suppose X and Y are varieties, they smooth varieties. And an F is a map between X and Y. Ask under what circumstances, or simply when, is it the case that for every differential form, top differential form, call it omega X on X, if you look at the measure, I'll denote the measure by absolute value. If you have a differential form, I'll denote the measure you obtain from absolute value. You have a measure on X, the QP points. Look at the push forward of this measure. Okay? You get a measure on Y, on the QP points of Y. And ask that, when does it happen that for every differential form, X, this measure has bounded density on Y. And this turns out to be a question about this turns out to be an algebrogeometric question. Okay? There is these were given by polynomial equations. There is some procedure, there is some algebraic procedure. I can play with the coefficients and tell you the answer. The answer up. This happens if and only if all fibers of F have, first of all, R. First of all, they have to be of the same dimension. Once you get one fiber, different dimension, not going. 2, they should all be reduced. So if you don't know, that's not an issue. And third, they can be singular, okay? Can be singular fibers, but the singularity should not be too bad. Canonical singularity. Okay, so if you have friends that do algebraic geometry, ask them. It's a well-known notion of measure of singularity. Okay, so I don't have time left, but what I want to say is that right, we started with a question about counting, right, representations. Translated this question to a question about measures. Then you translate it again to a question about algebraic geometry. And this is very useful, okay? So because it gives you access to techniques that you wouldn't have thought about if you thought about this as groups. Okay, you can start changing you start with a very concrete variety, but you can start change it. Other information. And in that case, Boudour, so what we could show, okay, so we showed is that this is true for G at least 20. Okay, and recently, very recently, Niro Boudour did it with a totally different method. Prove that this is true bigger than 1. Okay, so the corollary of this is that number of irreducible representations of SLD-ZP, little o of squared. And you can push it a little bit further, go to the discrete group, and show this is little o of n to the 2 plus epsilon for every epsilon. And this was quarter of my lecture. Thank you very much.